to this afternoon. We're going to continue our formal theme now. We've had Jasper, we've had one spin, and now we're handing over to Real Intent. And our speaker is Robert Eichner, and the talk is Lending a Formal Hand to CDC Verification, a case study.
Okay, thank you very much. I hope there's still some brain left for me after this long day of presentations. I'm obviously the last one. As Mike said, I'm from Real Intent. I'm the field application engineer for Europe for Real Intent. And the presentation today is about what beyond structural verification of CDCs can be done by using formal techniques, which kind of problems you can catch with them. And so the abstract is in the printouts, so I go for that. So the motivation was this year's DAC survey. So we did a survey among 300 customers passing by our booth at DAC. And the number of design starters, more than half of them is within the next 3 months. Just showing that turnaround cycles are going down, are more compressed. Then the number of clock domains, you see that 1/3 has 50 or more clock domains in the design, and means increasing the problem of verifying those. Then 2/3 of the customers stopping by had actually a bug in their CDCs causing a late ECO. And finally, 25% of the customers are thinking about introducing CDC verification into their flow, and 22 adding automated formal verification to their flow. And as that presentation is about combining formal techniques with structural CDC verification. So what the problem is, I think you're aware of what I'm talking about. If you have two asynchronous clock domains with a transceiving and receiving flop which are out of sync, which can have any relationship to each other, if the receiving clock comes along with a change in the data, your receiving flop might become metastable. It will take a while. With an undefined output, it might swing, and that could take one period or more to get back to a known state. And this is originally the problem we're talking about. So this is clock domain crossing metastability problem, and they are intermittent, hard to find, and if you find them late in the design cycle, they are hard to fix. There's a lot of stuff behind those usually then, including clock tree and so on. With synchronous CDCs, of course, you don't have these issues. You have others. Now, how to come along or how to tackle those CDCs, those clock domain crossings, to avoid metastability? You usually have design like that, which is a handshake synchronizer, and I have a control signal which is synchronized in. Then only the signal transition, there should be only one signal transition on this control signal for a bus, so it has to be gray coded. You have to check that. And it should be free of hazards and glitches, and it should be stable for more than one receiving clock cycle. So that only is a problem, of course, if your transmitting clock frequency is higher than the receiving one. The pulse width generated by the transmitting clock should be wide enough, or should be at least have the width of the receiving clock to properly get this signal clocked in. And you see here, in that case, we have a handshake, so it means we have a data path controlled by a mux or whatever you use for that, and the control signal is synchronized. So you have two synchronizing flops to avoid the metastability. That's assuming, of course, that if there's a metastability, you can't avoid them. You always get them at a certain point in time. If you have asynchronous blocks, you just have to take care that they don't propagate through the design. And then it could be that you need 3 flops or 4, depending on the frequency and technology parameters. There's a formula about that. There's a famous paper from Cliff Cummings from Sunburst Design, which is free to download. That's, for me, the Bible for flop domain crossing techniques and how to get control of those. The fourth one, the stable check for receiving clock cycle, that's a candidate for formal verification. On the other side, the data crossing, that needs to be a multi-cycle path, so to avoid any unstable stuff being propagated into the receiving flop, the rule is that this needs to be a multi-cycle path, and what that means is that if the data is stable, it should not be taken over by the immediate next following rising edge or next edge of the receiving flop. It should be at the second, it should be taken over by the second edge. And that's a check which can also be covered by formal techniques. Those 2 in green, this is something you cannot detect or cannot analyze using standard CDC structural checks. So on the terminology, what I said already, pulse width, that means that the control signal is up for more than 1 receive clock period, and that ensures that no data is lost, that the control signal is not lost as a data. And the data stability, that ensures that the captured data will not be metastable in the receiving domain. As I said, the important thing here is that it's a multi-cycle path, and not only from a constraint point of view, really from how the path is controlled, means that the data is taken over at the second edge. And transmit and receive, that's the clock frequencies and of that. So how is this CDC tackled in general? And this is for customers who do not use dedicated CDC tools. They build scripts around STA tools to move the edges and see what happens, try to provoke metastabilities in custom gate level simulation environments to see what is the design doing with this incident. And what's also happening is to verify the protocol, at least of these handshake circuit I showed you before, with an RTL simulation. That leads to that this kind of verification is usually done by the back-end or verification teams, not by the front-end designers. Those guys might not have enough insight into the design. It's a longer debug iteration because you work on the netlist, of course, and it's late in the flow, causing a long iteration cycle to fix this problem because you have to go back to the front-end design, to the front-end, run the simulations there, the regression tests, go through the implementation, and check it again there. So the recommendation, what we have in general, is use a dedicated CDC tool. So that way you can move this, or partially move this kind of verification into the front-end teams, because the verification itself is automated with a dedicated CDC tool, not breaking the rule that the designer should not verify his own block using his own rules, right? So, and why this should be leveraged, and also why formal techniques make sense. This is the item of a case study which we did, an experiment, and we used the some kind of modified handshake design I showed you before. So the two components here you have as a design option. This is the control logic I have generic here, and the detector. So the control logic can be a counter-based, it can be FSM-based, it can be a pulse stretcher. The detector can be signal transition-based, like in the design I showed you before, and what we use in the case study. It's a simple XOR gate, which you call an edge detector. Or it can be finite state machine based. The variables in the system is the clock frequency and the ratios of these clocks to each other. It can be the sweep, how they are shifted, and also an important factor is the reset timing. So especially when is the reset release, and to which clock is the release synchronized? Is it synchronized among all clock domains, which is usually not the case, or do they have an offset in release, and will this lead to problems as well as if you do not, if you cross with the reset signal a clock domain, you can also cause metastability, having the reset change at the same time the clock edge shows up on the receiving flop. So what we did is we took a counter-based control logic, a low to high transition detector, simple XOR gate, and the resets are aligned, so we're taking the easy case here. And for different ratios on the pulse width check, for different ratios on the clocks, the pulse width check based on different counter values is listed here as a good fail case. And as you see, if I have a ratio of 2, I need a counter starting with 6 to have enough width, pulse width on the control signal. If I increase the frequency, then of course, and this was as expected, the counter value, the necessary, goes up. Right? So this is pretty straightforward. 5 minutes? Okay. I will do that. Thank you. So if you look at the data stability checks based on the counter value, you see that this is not obvious. So you have for counters, for a ratio of 2 for a counter, 2, 3, you have a fail, 4 works, and the following do not work, and then from 10 on it works again. And you have the same phenomenon for other ratios. So that means, like for a ratio of 5, for instance, you cannot assume that if a counter value of 10 passes, that 11 passes as well. Right? So it's not straightforward like the pulse width. So like the fail case for counter 14, and of course the counter width is important to, as it defines the throughput of your CDC. Right? The smaller the counter value, the faster the data throughput of your CDC. And now for a counter value of 14 and for a clock ratio of 3, you see that what we can generate is the fail case values. So and you see that in that case the data stability check fails. If you look at these 2 dotted lines here, I don't need to jump. So you see that the control goes high of the 2 edges. The edge detector, the detection logic goes high, opens the mux. And in that case, data changes at the boundary when the counter goes from 14 to 0. Data changes. Data is held stable, of course, for the whole turnaround of the counter. The control changes at half of the counter value, goes up to let the data through. And you see that the edge which is taken over the data is the immediately following edge after the data changes. And this is a failure. Right? This is why this is a fail case. For a counter value of 16, which also fails, you see that there's a good case, and then it also fails at the immediate edge. taking over the data. Case of 15, I don't have a waveform because we don't yet show the good case, but it's I would have to draw a waveform, but it's simply because the counter counts up from 8 to E, and that way, if you would change here at 8, then the control signal goes high here, and it's better aligned to the edges, so it's hold on longer. The mux is longer on, and that way the data is taken over properly. This is why we have a good case with 15, bad case with 16 again. Now, if you also now start to move the offsets of the real resets, you have some kind of you also have impact on the pulse widths now. Remember, with aligned resets, we had simply pulse widths getting under control by successively increasing the counter values. Here, the pulse width is also not, let's say, linear, or you just increase the counter value and you have a good case, right, as you see here. So the benefits for that is you can experiment with this. You can tackle your design, because, like in that case, 15 passes. But if you then do a slight change in clock frequencies, in reset alignment, you might immediately have a failing case. And if you detect that in the back end, or if you detect that at all in the, let's say, netlist verification, that's a long way back to then change the counters and test them out whether it works or not. So you don't need a deep understanding of the design. It's simply a push-button thing to get there. It saves backend and CDC verification time, streamlines design flow, and design exploration. The design engineer can explore his design and try out different values to see that the design is stable. Okay.
Thank you.
Okay.
Any questions? No, thank you very much, Robert. Just one quick question for me. So the designers actually users, are you advocating that designers actually do their own CDC verification and not involve verification at all?
Oh, what was, I didn't get it.
If the designers can do this themselves, then can we actually take the verification out from that particular part of the design, would you say? Going back to the conversation we had earlier, where a JL proposed quite radically that less verification engineers equals higher quality. Is this a way of doing that, would you say?
It's a point of view, right? I have customers where the verification guys in the back end or on the net list said now they can prove that there's really a problem, even if the designer tells them there isn't, for instance. That's one thing. And the other way around is that it's really like I said here, that's something every designer can do without struggling or having lots of, or need to simulate or customize a test bench or whatever. So it's really a push-button thing to test out if his CDC is stable. So.
Okay. Okay, thank you very much.